Starts with Sergei Odintsov from Barcelona, talking about unified accelerating cosmology, modified gravity, new models.
Okay, so today I'll try to give some review about cosmology based on modified gravity. I'll be mainly talking about FR gravity. You already heard during the several days about this model. So first I give some brief, maybe 15 minutes introduction. So most of things eventually some of you who are working in the theory do know. And after that I'll talk about different extensions of such model and about different possibilities, new possibilities for cosmology we can get out of that model. So let me start from just brief motivation. We want to have gravity-dominated evolution of the universe because for me, aesthetically, it looks not nice when we have one scalar field to describe inflation, which we try to identify with Higgs field. Then we have another scalar field to describe dark energy. Then we should invent a scenario how one scalar field disappears and another scalar field appears and becomes relevant at late time. That is the reason why we try to use only the fact that we have gravitational force, so we want to use gravitational interaction to describe the whole universe evolution. Of course, that is a dream, but some success on that already has been achieved. So you know that inflation may be described in frames of modified gravity quite easily. A square or Stravinsky inflation, which is one of the first models which appeared in 1980, effectively still remains, as it was even repeated here, one of the best inflationary models. Apart from that, we also may consider more complicated high derivative gravities, non-local gravities, Gauss-bounded gravities to describe inflation. However, FR gravity continues to be most simple, despite the fact that it's quite a complicated model. And it's perhaps not surprising that precisely the piece of R gravity, so R square gravity, which is dimensionless, plays so important role for description of inflation in 4 dimensions. For last 10-15 years, we also know that dark energy may be also described by some modified gravity, which may be also FR gravity, Gauss-bounded gravity, non-local gravity, etc., etc. So we have a lot of choices. So currently we have too many theoretical models even within modified gravity theory, and we quite well describe the lambda-Cilian model due to lack of observational data still, which may reduce the number of theories. So as I told, the most interesting possibility is to describe complete universe history, starting from inflation, then radiation matter dominance, and then dark energy within the same theory. And as I will show, that is possible to do not only in FR gravity, that we did many times for many variants of such theory, but also it's possible to do for other extensions of such theory out of the graph. Additional benefit of modified gravity is that we can get dark matter from modified gravity. There are different ways to get dark matter. The simplest way is, as we have, for example, even in FR gravity, we have scalar degree of freedom. We may associate dark matter with such composite scalar degree of freedom. The fact which supports such point of view of gravity-dominated evolution of the universe is that we can pass local test and viability conditions for number of modified gravity. And finally, despite the fact that this approach remains to be phenomenological to large extent, we may hope that at least some versions of such theory may be obtained as effective theory from quantum gravity theory, from string theory. In that respect, quite interesting is that high derivative R-square gravity, but full R-square gravity, which contains all R-square terms, which are permitted and which are independent. So in 4 dimensions we have 2, may be considered as quantum gravity and may be used for unification of gravity with grand unified theory. So we have quite appealing possibility that modified gravity may be viewed also as quantum gravity. So it may be related in one way or in another way with quantum gravity. And I'll mention also about alternatives to standard universe evolution, about bounces, and we will see that it's also not so difficult to describe bounces in terms of modified gravity. So just several well-known facts. So we start from the model of that sort, where we have FR gravity plus some matter. And a convenient way to present such theory is to consider general relativity plus some correction. And in this presentation, you see that the model may be understood as kind of dynamical cosmological theory, so as kind of solution for dynamical cosmological constant problem. Equations of motion may be presented directly by variation, or many peoples they do as a representation of the following. So trying to mimic usual Einstein relativity, so left-hand side should correspond to Einstein gravity and the right-hand side should correspond to something else. As you see, in this case we have the following problem. So many people who are doing this, they forget, and even here I heard they forget that doing this you have gravity from both sides. So it's not energy momentum. Even matter is not energy momentum because in front of matter energy momentum Lagrangian we have the contribution of modified gravity. So this representation is good when we study background evolution, because in that case we can use a lot of knowledge we got in the study of general relativity. However, this representation is not good when you start to study perturbation, when you start to study black holes, when you start to study stars. The reason is very simple. I will mention about this when we talk about scalar tensor presentation of this theory, but simple reason which immediately you may start to think about is think about energy conditions. Energy conditions in this formulation. What is energy conditions? So you apply it to this side, but here there is also gravitational side. So you should start to think about new energy conditions using correct gravitational formulation where all gravity part is on left hand side. So sometimes this convenience puts in a lot of problems. I will mention later on about this. Nevertheless, sometimes it's convenient, and as I told, it may be good for background evolution. So this description is definitely okay for background evolution. Unlike the usual general relativity, trace of FR gravity is non-trivial equation. And from the trace equation, which we can rewrite in this form, we see already from this presentation, we see that there appears effectively scalar field. So forgetting about any rewriting of the action we see from this presentation, that we have effective scalar field, which is sometimes called scalaron, and this effective scalar field may play an important role in the theory. In fact, precisely this scalar field sometimes may be identified with dark matter, providing the possibility to unify not only two accelerating pairs of the universe, but also dark matter within the same modified gravity. So we may study the properties of trace equation. In particular, we may study the perturbation around this equation. So when we consider this equation, we do the perturbation, for example, the first order of curvature, and in this way we have quite complicated equation, which is useful, for example, to get to pass spherical body solution. So to get correct spherical body solution as we have in general relativity. Another interesting property of that is that here we get effective mass, which is given by this expression, and effective mass of this scalar mode is precisely in inverse gravitational coupling constant, so Newton constant. I'll talk mainly today about Friedmann-Robertson-Walker universe, so flat Friedmann-Robertson-Walker universe. And as I told, we may use description where we write general relativity with effective fluid, but this effective fluid is given by modified gravity piece, so modification which enters to action. Because mainly I will be talking about background evolution, that is okay here in this theory, but in some cases we may go beyond. So the remark about modified FR gravity theory is the following. It has been also said here during first couple of times, and it's getting kind of everybody knows story that FR gravity theory we can rewrite as kind of scalar tensor theory. So it's quite common to say that this theory is just the same as FR gravity theory, and it's not necessary to study modified gravity, and it's enough to study scalar tensor theory. So eventually everybody of you saw many papers which say cosmology of modified gravity, cosmology of FR gravity, where people write the section, then switch to scalar tensor theory, and after that forget about modified gravity and work only with that action. Effectively, this brings to a lot of problems, and in many cases it's incorrect. The reason is very simple. Even without matter, we have inconvenient description of physics in these two different frames. For example, accelerating cosmology in this FR gravity description may be decelerating cosmology in this description, and vice versa. Inflation in this description may become bounds in this description. Geometrical objects should be treated extremely careful in these two descriptions. Because what looks like wormhole in FR gravity may not look, in some cases, as wormhole in scalar tensor theory and vice versa. So, even mathematically, in order to transform from FR gravity to conformal transformation to scalar tensor theory, we do conformal transformation. However, when we do conformal transformation, we consider the whole space-time. Okay? And there are many cosmologies where we have singularity. There's a Big Bang singularity, Big Rip singularity, etc., etc. So when we apply a conformal transformation to such cosmology, even mathematical equivalence between two theories is broken. So mathematical equivalence is broken, so these two theories are not equivalent anymore. When we add meta theory here, we have the problem because when we make conformal transformation, our meta sector couples with conformal factor. So when it couples with conformal factor, we eventually should rethink our standard model of elementary particle physics so that we should take into account the coupling with this new scalar field. So it makes other complication in the theory. So even if it looks so simple to do transformation from higher derivative theory to more simple second derivative scalar tensor theory, in practice it doesn't simplify theory at all. The reason is that for all interesting models of FR gravity, except of R square gravity, which is one of actually exceptional cases, if we have simple form of FR gravity on that side, on scalar tensor side, we will get very complicated potential. So, for example, for R cubic potential, we will have here couple pages expression, and vice versa. For simple potentials in this way, in this formulation, we have quite complicated expression for FR gravity. So, one should be extremely careful doing this change of frames. However, there is one special case when it's fully justified. In this case is inflation. When we study inflation, we consider quasi-de Sitter universe. So for quasi-de Sitter universe, you can show explicitly. So you can do calculation of all quantities in both frames, and you will see that calculation of indexes, for example, in both frames, is just the same. So that is de Sitter and quasi-de Sitter. That are the spaces where it's quite possible to change one frame by another frame in the description. So one example of the theory which unifies inflation with dark energy is our model which was proposed several years ago, and that is exponential model, where we have exponential sector to describe dark energy. We have another exponential sector to describe inflation. And we have power law term, where this parameter often should be around 2, so that to get exit from inflation. So that is the model which, as I told, when we consider this function, it gives kind of dynamical solution for cosmological constant problems, and at the same time, it gives the possibility to unify the description of dark energy with inflationary tempo. So, without going into the details of that theory, we may consider, for example, the following choice for the parameter. So, parameter n and parameter alpha in this theory. So, that is parameter n and that is parameter alpha. And we will set the inflationary scale as equal to cosmological constant or at inflationary time. And then we can work with Friedman-Robertson-Walker dynamics. For example, we can work in terms of this coordinate. So in this coordinate, we have the following definition of this coordinate is dark energy pressure divided over energy pressure of matter. And we introduce mass scale as the following, and parameter x, which is defined as the following. And we can get sometimes used form of description of Friedmann-Robertson-Walker equation. And then we have quite large number of parameters here. As I told you, it's kind of phenomenology, so it's not so difficult to fit the prediction which are typical for effective lambda CDM epoch. So for example, for this choice of parameter in this equation, we can get the possibility to have dark energy effective equation of state parameter around -1, which is quite well with predictions of usual lambda CDM model. So that was just a reminder about one possibility to variable modified gravity model, which may unify inflation with dark energy, and in principle also with radiation and meta dominance. But in that case, we need several more terms to add to the theory, plus to take into account meta. So that was kind of the introduction, and now I'll start to talk about kind of extensions of this theory. So, any questions about that? Yeah.
Issue. You've got extra. You put a number of parameters.
Yeah.
Right. So one of the objections, of course, against the concordance model is there's a lot of arbitrary values. You stick it in cosmological constant. There's some dark matter.
Okay.
There's a lot of ad hoc stuff, and so really you gain nothing.
What do you mean?
You have a much more complicated
It's rather philosophical question. Just the same we have with usual lambda CDM cosmology. We have a lot of parameters, and we play with these parameters, and we try to fit with observation. And just the same here. You have this theory, you try to fit this theory with observation. And for example, I guess you didn't follow the development of this theory.
No,
but
I followed the development of the theory.
but eventually you could see that each several months, especially at the beginning, they appeared the claim that this theory is incorrect because it doesn't fit with this. This theory is incorrect because it doesn't fit with this. Now we have quite huge region of parameters, and we, I mean, it's not region of parameters, it's class of theories. As I told, it's kind of phenomenology. Some of the models may be predicted by string theory. So, if aesthetically you don't like it because you spend more time studying scalar field, it's up to you. But in scalar field, it's the same, a lot of choice related with potentials and parameters of this potential.
Yeah. You have a parameter in there, a dimensional parameter, which you must have, which then must be of the order of the whole, before we get into the inverse Hubble rate.
Yeah.
Right. Which is what the cosmological constant is. You're not explaining that parameter. Then you have another one to handle the dark matter, which is quite different.
Yeah.
So I'm saying, in your theory, which is much harder to deal with, right, involves a lot more work.
For you, much harder. For me, much easier.
No.
So it's a question of convenience.
Not that you work for me, but for the people, the large community, who just looks at the concordance model and says, I'm satisfied.
Okay.
And I'm going to base my observations, I'm going to base my analysis from the SKA on that, and then finish the clock. And they don't look at these things.
As I told, that is kind of phenomenology as any model, as any cosmological model for the model.
Okay.
So any cosmological model, you will get just the same.
Does the kinetic term for scalar field has...
There is no scalar field here.
No, for...
So there is no scalar field here. Technical questions at the end.
No, I mean
Where is
effective scalar.
scalar field?
No, I mean F of us gravity.
F gravity, that is modified gravity. There is no scalar field here.
Yes.
Now I will start to talk about scalar.
No. You said that this model is effectively, in some sense, equivalent to metric plus scalar field.
No. I didn't say that. I thought that in a way there is composite scalar degree of freedom. That's all. Which you may understand as kind of composite scalar. That is not elementary scalar. It's another story. That is internal spectrum. Furthermore, other models of modified gravity, they do not have this property. Okay, so I will start to another version of the theory, which is called mimetic gravity. So eventually, as you heard, some of you may hear in the course of usual general relativity, since long ago there was the dream which Hermann Weyl was trying to realize, and that was to implement conformal symmetry in cosmology. So to prepare, to suggest a model which is conformally symmetric and which works well in cosmological context. However, when we try to do this, we know that while gravity, conformally invariant gravity does work because there is no nice and natural way to describe Friedmann-Robertson-Walker dynamics in this theory. There is a possibility, nevertheless, to implement conformal symmetry, but as a fake conformal symmetry in so-called mimetic approximation, which is done as the following. We consider usual metric, and we parameterize by hand this usual metric in such a way that we introduce, so Misha, that is now we introduce by hand kind of scalar. Okay? So we introduce here scalar, and we introduce here new metric. And now from that point, after introducing this, we will start to consider the variation of our action, of our FR gravity action, not with respect to G mu, but with respect to new metric and with respect to new scalar. Okay? So this parameterization is invariant under Weyl transformation. So doing so, in this parameterization, we'll get the theory which has conformal invariance. Okay? So many people suspect that conformal symmetry is fundamental symmetry. We know it's related with string theory, for example. But also it should appear somehow in cosmological context. So we consider then this theory instead of usual FR gravity. As you see, we still consider same theory. However, just by this artificial parameterization of metric, we get scalar. So this scalar is not usual scalar, not scalar which we add in the theory. This scalar is better considered as kind of gravitational partner. So making variation is not so easy. We get Friedmann-Robertson-Walker equation, and we get scalar field equation. So important property of such mimetic FR gravity is the following: that these equations, these two equations, they are always satisfied in convenient FR gravity, and then trace equation is the same. Then any solution of convenient FR gravity is solution in this theory, but the contrary is not right. Another interesting remark is that FR gravity is ghost-free, and as I told, conformally invariant theory. So this mimetic FR gravity is ghost-free, like original FR gravity, and that is another reason why a lot of attention is paid to convenient FR gravity. Now we work with usual Friedmann-Robertson-Walker cosmology, and we study scalar field equation. So working with scalar field equation, we get the following term, and this term is typical for Haraba-Lifshitz gravity and for brane-walled systems. Okay, so when we work with this first Friedmann-Robertson-Walker equation in this metric, we arrive to the following equation from TT and the EG component. And combining two these equations, we will get simple equation which should describe dynamics of our theory. So eventually we have the following. We have modified FR gravity, which admits unification of inflation with dark energy. However, We also have cold dark matter here, which has totally geometrical origin. So the way to understand just the same theory in other terms is to work with Lagrangian multiplier constraint. So working with Lagrangian multiplier constraint, we introduce the following term to our F gravity. And in this way, making variation over lambda, you will see that this constraint gives precisely the same condition which we have here. So this is, say, more comfortable, more convenient way to describe in covariant form such a theory. Also, as we have now kind of scalar tensor theory, even that is not real scalar tensor theory because kinetic term is somehow degenerate due to the fact that this scalar field has no kinetic term. We may add by hand scalar potential, and in that way we have even more freedom to describe the observable universe history within such theory. In fact, we constructed a number of models where we may get unification of inflation with dark energy, and also with including via this term including dark matter, which are consistent with observational data, at least with most important observational data. Some further indication may be, of course, important here. I will not go further in details of the theory because they're quite complicated. But background dynamics is just the same as in the F gravity I just described.
So the light cone structure in these gravities are given by G mu nu or G hat mu nu, which one? The causal structure.
That is another form. That is another form of the gravity. So in this form, you may forget that you have two metrics.
Right.
Simply.
Yeah.
So you have just one conformal metric. Sorry, covariant metric. Forget it. So that was just to show two equivalent places. Now, the next story in modified gravity may be related with singularities. So, Miriam, she likes singularity very much, and she will talk about that. So I will not talk much about that. But I only mention that in principle, in the universe, we know that our universe eventually started from Big Bang singularity. And due to the fact that we have dark energy accelerating cosmology, our current universe may also enter to one of these several singularities. So that is typical singularity which is related with phantom evolution. That are singularities which are related with quintessence evolution. And there is also some minor singularity where we have at the read point, we have all important cosmological parameters finite, but high derivative of Hubble rate, or in other words, say square invariance of Riemann tensor may diverge. So there is the following type quite weak singularity, which is called here type 4 singularity. Of course, it's not the whole story. We do not know what's going on in the future of the universe. So it may happen because we don't know what is the current equation of state effective of our theory. So apart from these possibilities, the universe may change acceleration to deceleration. It may approach de Sitter. It may enter infinite singularity. It may approach de Sitter being in phantom region. So all the time below -1 barrier. So there are many interesting possibilities. However, related with this singularity, I wanted to bring attention that there is a possibility even to rethink the usual inflationary scenario, which appear, which is eventually most common scenario for early universe. And that is so-called singular evolution, which was considered in that works. So that works as the following. I'll give the example based in scalar tensor theory, but the better realization is in modified for gravity, which I will explain now. So if we work with usual scalar tensor theory, so now forget about modified gravity, that is just example to show specific type of singularity of inflation. So we put here another scalar potential just to permit here transition from canonical to non-canonical kinetic terms, so from canonical to phantom region. Imagine that we consider the following evolution of the Hubble ray, and in this case we have the possibility to describe type 2 or type 4 singularities. So that is type 2 singularity and that is type 4 singularity. So for simplicity, we may take this function equal to 0 and this function equal to constant. And then we can reconstruct this scalar theory for this cosmology in with this choice, so that we get specific potential. So specific potential. So that is potential in terms of this scalar, and that is potential in terms of canonical scalar, when we redefine scalar so that to bring this potential in the definition of new scalar field. So that will be scalar potential, which precisely describes this this type of evolution. Okay. So then with the following conditions on the parameter alpha, we get type 2 singularity, and with the following condition to the parameter alpha, we have type 4 singularity. And then there appears several possibilities. We may study inflation with the type 4 singularity, which occurs somewhere during inflation. Or inflationary area may end with type 4 singularity. Or type 4 singularity may occur after inflationary area. So second and third cases are more realistic. And now let us consider which consequences of such modification for usual inflationary cosmology we may get if we consider such form of singularity. So, as an example, we may consider the following evolution. So the following evolution, and we want to get the description of singular inflation within F gravity. So we consider this evolution with the following conditions: that this parameter is much bigger of this parameter, plus this parameter is also much bigger than whole second term for alpha equal for alpha positive. So then this description is just quasi-de Sitter evolution of the universe. Now, as I told, we are interested in realistic evolution in such a way that type 4 singularity occurs. As we see, this type 4 singularity occurs when this parameter is bigger than 1. Okay? Now, we try to describe such evolution in frames of F gravity. So we do as the following. So we consider F gravity. We write the equation of motion. So in this case, we get, because we work without matter, we get single equations of motion. And to this equation of motion, we substitute this evolution for Hubble ray, so that to reconstruct the form of F gravity, which will describe our singular inflation. there are different ways to do this reconstruction, but one way is that we may use auxiliary scalar field. So we rewrite this function, this action as the following action, so that making variation over scalar and redefining and finding the solution of this equation in terms of solution for scalar in terms of curvature, we'll get precisely FR0. So working here with such description of FR gravity, we come to master equation, which should describe Friedman-Robertson-Walker universe, and we substitute here, as I told, the Hubble rate corresponding to singular evolution. So substituting in here and solving here, we rewrite this equation as some equation which has solution in form of some special functions, and this for this equation, the approximate solution is R square gravity. Okay, so for R square gravity, we may get, but not exact R square gravity, with some corrections, which we don't write here. We can get singular evolution. So let's now compare the inflation for usual R square gravity and inflation for such FR gravity, which is approximated by R square gravity. So we study Hubble flow parameters, and we consider usual R square gravity. So we study Stravinsky inflation in this case, and we describe quasi-de Sitter universe as the following. In this case, we calculate parameters here, introduce a false number, and I will not go into details here as they're quite well known. So we arrive to spectral index and scalar ratio, which are within Planck data. So here we have nothing new. Now, we do just the same game, but for our FR gravity, so that we want to consider the case of singular inflation. In this case, we have some modification of the perturbation over de Sitter solution. So small perturbation. So we work with such theory. We study again Hubble flow indexes, and we see that one of these indexes remain to be the same, while another index is simplified a little bit, and the only difference is with this index, which becomes singular at every point. Okay? So we see that this Hubble flow parameters, which control slow roll expansion, they indicate that there is dynamical instability of the system, which is different, qualitatively different from usual R square gravity. Okay? So now we may compare, from one side, this instability may permit to system to describe the exit from inflation, and from another point, it may change something. When we calculate again inflationary parameters, we see that they're just the same. However, when we calculated them, we get just the same parameters for smaller value of e-folding. Okay? So we get smaller value of e-folding, but in that case, parameters are the same. And we get that in this case, we have the following qualitative result. We have usual R square inflation, and we have singular, nearly R square inflation. And the type 4 singularity we have here doesn't show any observational implication to the indexes which we calculate. Only e-folding number is changing. However, the new qualitative feature is that this scenario ends early, and there is a possibility for more abrupt exit from inflation in this case. We may consider even more complicated case. So we may consider, for example, the possibility to describe whole evolution of the universe. So when we want to include here, in this specific case, we want to include inflation, we want to include late time acceleration, and we want to include at least matter dominance for simplicity, and to describe it in qualitatively simple way. However, there is also a possibility to add one more term in this Hubble rate, so that to get also description of radiation era before matter. So working with this Hubble rate, we may reconstruct again the evolution of the universe in F gravity in this case, so that not only one but type 4, but two type 4 singularities that gives some restriction to the parameters of the theory, so that two type 4 singularities occur, one type 4 singularity occur at the end of inflation, and one such singularity occur in the middle of matter dominance era. So in this case, the interest is the following. In principle, unlike to these singularities, which, as I told, they are studied in quite a lot in the literature. In this, for this type of singularity, actually there is no singularity, even we call it singularity, because geodesics may be continued consistently, so the corresponding point, and there is no any dramatic consequences for that. So again, we choose the number of parameters, but in this case, we try to mimic the history of the universe. So we choose these parameters in the Hubble rate, trying to put whole history of the universe within say single function. Of course, it's approximation, okay? But in this case, it's not let's say it's not the model parameter. That is parameters of the evolution function. In this case, Hubble rate. So we may see that first term. So first term here is called inflationary, describe inflationary universe. Then we have third term, which is constant at early times. Then we have the dominance of cosmological evolution by this equation, by this last term. So that will give us description of matter-dominated era. And now we also may check by calculation of effective equation of state parameter for all these three errors we try to invert in universe evolution. And we will see that at the early time, the equation of state is approximately -1. After that, equation of state parameter is changing to be around 0. And at the late time, it's again described nearly de Sitter universe. So the lesson for that description is that in principle, within modified gravity, we may try to show the evolution of the universe from inflation to late time universe, including radiation and matter dominance. So I have a couple minutes, so I wanted to talk a little bit more about unimodular theory, which is another generalization of F gravity. So unimodular theory is a theory where we have the following constraint, and this theory was suggested many years ago to solve the cosmological constant problem. And this unimodular theory may be again understood as usual FR gravity with mimetic Lagrange multiplier. However, now we see that because of the fact that in front of this color we don't have square root of metric tensor, this theory is non-covariant. Plus, we may consider any power of metric determinant here. So we have class of this unimodular theory. And we may also describe evolution of the universe and the unified evolution of the universe within such theory. There may be several questions here. So first question is, this theory seems to be non-covariant, so people does like usually this fact. The answer to this question is the following. In fact, we may work a little bit with such theory and present it in covariant formulation if we introduce higher rank tensors, just auxiliary, of course, just in the same way as it was done for original unimodular general relativity. And in this way, we get totally covariant description. However, the interesting fact is that equations of motion are the same. Nevertheless, there is some qualitative difference in the description of Newton's law. For example, for non-covariant unimodular gravity, we have Newton's law, which is just the same as usual general relativity, while for covariant unimodular FR gravity, we have Newton's law with corrections, like in usual FR gravity. So I don't go to this theory. So here is the calculation of example and calculation of inflationary error within such theory, and for specific form of unimodular FR gravity, we again choose the parameters. In one way, we get consistency with observation. And so that is example of unimodular FR gravity which satisfied to inflation with observation of data. So the same game we may repeat in the study of bounces of FR gravity, but I have no time here and I have to stop here. But the conclusion of all this description is that even within simple FR gravity theory, which is eventually simplest theory from non-modified gravity, we may describe the whole universe evolution from inflation to dark energy with quite high accuracy and without the need to consider any extra fluids and any extra scalars to describe one of acceleration error or even dark matter problem. So let me stop this.
Thank you, Sergei. Any questions or comments?
You defined type 4 singularity in terms of Hubble parameter, which is not a scalar. Is it possible to define
Yes, I thought
this?
you can define this in terms of invariance, for example, I mu alpha beta squared and some power. Yeah, it's written.
The definition?
Yeah, it's written.
Okay.
Yeah, here it's not written, but in the paper.
I am.
For the type 4 singularity in the past, before inflation, what happened there is superinflation, something like, I mean, when you are approaching type 4, you have H dot positive.
We studied type 4 singularity after inflation, but not before inflation. So that may be quite interesting possibility.
This is a way of avoiding the big bang, so
What?
you have something smooth. That's why I thought.
No. This singularity may occur at the end. I mean, that is theoretical possibility which is admitted and which doesn't change observational indexes, nothing else. So the benefit of that is that we may get exit then from inflation even without R squared term. For example, you know that in FR gravity without matter, the exit for inflation is R squared term. Now, with type 4 singularity, we may get exit even without R squared. So that is possibility as I know. It change only the exit properties, but not observational indexes. So it's in a sense it's minor.
Okay, sorry, my question was.
But about type 4 singularity before inflation,
Yeah.
we simply didn't consider anything about it. The point is that here you should take into account quantum gravity. And quantum gravity, you should use effective action, which is obtained from quantum gravity. At least this form of FR gravity, I may argue, may appear from some compactification of string theory, so you may already rely on classical descriptions with taking into account of some quantum properties. But before inflation, we should take into account quantum gravity completely. So everything should be changed.
Yes.
In the unimodular gravity, what is the background space-time? Is it Robertson-Walker?
Yeah.
But in that case, minus root g is not.
Yeah. But you can write very good observation, and the point is that in order to have consistency with this constraint, you should use not this form, but you should use unimodular method. Simple. Or you may forget about all this, and you just work with Lagrange multiplier constraint. Simple. So you see, even making very minor variation of FR gravity, you have quite rich dynamics. Completely different.
Could you falsify these theories through structure formation, for instance? I mean, because
that was not done.
It seems so.
Yeah. It was not done, but of course it's not big problem because you have just extra scholars. So you should, to usual study, you should add the contributions from the scholars. It's numerics.
All right. Great. This time, Sergei again.